Hello, welcome to N42, continuation of kinetics focusing on instantaneous rate and the rate law. Take a moment and copy the target. All right, we are back. All right, so let us begin this discussion with instantaneous rate. So what is instantaneous rate? Well, we saw last time that the average rate tells us the speed of a reaction over 2 time points. But what if we want to know the rate at an exact time point, or only one singular time point during a graph? Well, we have to calculate the instantaneous rate. So, let's look at this reaction. Here's a graph of that reaction as the reactant of C4H9Cl is decreasing over time. So we can plot concentration versus time, as you see here to the graph on the right. Now, when we're looking for instantaneous rate, the slope of a line tangent to the curve at any point represents the instantaneous rate. Now, the tangent line at any given point is the first derivative. Welcome to calculus. But, we're not doing calculus here, so don't worry about it. We are literally going to be hand drawing the tangent line into our graphs. As you can see here on the right graph, the beige color one is touching this single point, and the blue one is touching this point. I know there's no black dot there, but again, the tangent line is a line that touches one single point. It does not cross the graph, it touches a single point. Any questions on this so far? Okay. So, as we just said, the instantaneous rate is equal to the slope of the tangent line to the curve at a specific point. So here's another kind of blown up example. Different reaction, doesn't work. Don't worry about that fact. But again, it's this blue line that is drawn in at time equals 2, is what we're kind of the point we're focusing on. Now, the tangent line, again, a straight line that just touches the curve. Again, it does not cross the curve. It's touching the curve only at one point. We also need to remember the slope of a line is just rise over run. So as long as you have 2 points of this tangent line or straight line, you can find its slope. We cannot be sloppy when we draw in the tangent line. We have to make this as straight as possible using a ruler, using a straight edge, using something. No, it's not exact when you are obviously using a ruler to do this and the thickness of your pencil. At the end of the day, calculus is your best bet. But again, we're not doing calculus, excuse me, so don't worry about it. Questions about how to make a tangent line? Okay. Easiest thing when you do draw one in is draw it long enough so that you cross or touch the x and the y axis. The one point you always have is the exact point that you're using. So this point right here, you always have that one. And then you can use the y-axis point, or you can use your x-axis point as your second point to find rise over run. All right, so continuing with our instantaneous rate, same reaction we saw before in our graph. The reaction slows down as time goes on because the concentration of reactants is decreasing. So that's kind of an always thing. The reactants have to slow down because you're using them up. So here we can see kind of a different slope, if you will, compared to this area on the curve where the slope is changing due to a decrease in concentration. Keep in mind, a steeper slope equals a faster reaction or a faster rate occurring at that time. Questions? Alrighty then. Alright, so practice problem. I did post this on the one-stop shop for you guys to get. So if you can cut this out and put it into your notes or use it and then paste it in later. Either way, we want to have practice here getting used to drawing in our tangent line to the curve and calculating our instantaneous rate. So let's take a moment. If you can grab that, that would be very helpful for you guys. Alrighty then. So here we go. What is the instantaneous rate at 30 seconds for the decomposition of hydrogen peroxide? So here's the graph that you should have, that you printed out, hopefully small enough that it'll fit into your notes. Now, find 30 seconds. There's our point. You guys can, draw a little bubble, if you will, or a mark to make sure you know where 30 seconds is. Take a ruler, and we're going to draw in a tangent line. Now, again, you can extend it all the way to the y-axis or the x-axis. I did not for this example, but it does and can help you if you do. So that's my tangent line, the black line. All right. So I'm going to draw on my little triangle here. For me, again, if you went to the y-axis or the x-axis, that's fine. I did not. Doesn't make a difference. It's still, I need 2 points in order to get the rise over the run. So here's my rise and my run based on what I came up with. And this gives me my reaction rate of a negative 0.015 molarity per second. So it's pretty straightforward in that sense. Again, you're probably going to be a little bit off that number, which is fine if you went all the way to the y-axis or you went all the way to the x-axis and chose those points. Again, this is a kind of rough and down and dirty way of finding instantaneous rate without doing calculus. Any questions on this? Alrighty then. All right, we are done for today. We're kind of starting it here, and we'll pick this up on our next class period, where we're going to get into rate laws. All right, we are back for rate laws. So, the rate law, really just an equation that expresses the mathematical relationship between rate of a chemical reaction and the concentration of reactants. So our two kind of variables here, rate and concentration. That's our focus of what's going on. Excuse me. So here's a general reaction of A plus B going to C plus D with their coefficients. When we write our rate law, this is the generic form, rate equals lowercase k, yes, lowercase is specific, do not make it capital, multiplied by the reactants raised to some power. Notice again, reactants are used in the rate law. So anytime we write the generic reaction, generic rate law for any reaction, we always just use the reactants. There could be 1, there could be 3, there could be 37. It doesn't make a difference. It's still set up the same way. Rate equals lowercase k times the concentration in molarity of your reactants raised to some exponent. Now, x and y, or you raise it to whatever coefficient, whatever letter you want. Doesn't really make a difference. Questions on writing a rate law? Alrighty then. Now, reaction orders. These are parts of the rate law we just saw. So here's our same generic equation with our regular rate law. Now, these exponents that I have just circled up here with x and y represent the the reaction orders. Exponents are the orders. So these exponents in the rate law tell us a few things. First thing, the order with respect to the concentration of that reactant. So in this case, X is the order of A and Y is the order of B. Again, any letters you want to use doesn't make a difference. X, Y, Z, A, B, C, whatever. But interesting thing is, what does that mean? What are these orders? What do they do? So the order is a mathematical effect an individual reactant's concentration has on the overall rate. So the question that's kind of proposing is how much does a change in concentration affect the overall rate? So if I know what the numbers or the orders are for X and Y, and I change the concentration of A and or B, what effect will that have on the rate? That's what these orders are going to help us to understand. Question about this so far? Okay. So how do we talk about it? How do we discuss these reaction orders? Well, we can say that the reaction is Xth order with respect to A, and the reaction is Yth order with respect to B. Kind of already went over that a little bit. But then if we add our orders, individual orders together of X plus Y, we get the overall order. All three of these, the orders with respect to each reactant, as well as the overall order, are important aspects of the reaction and rate law that we are trying to determine. Questions? Okay. Well, what is this lowercase k thing? Here's our reaction and our rate law. Nothing's changed. Lowercase k is called the rate constant. Again, I'm going to emphasize this. It is a lowercase k, not a capital K. That's our next topic. Yes, I know. Same letter, different capitalization versus lowercase, meaning completely different things, but welcome to chemistry. So back to the lowercase k, which is the rate constant. It's basically a fudge factor. It's a numerical value that relates our reaction rate and concentration at a given temperature. Remember, everything is temperature dependent except nuclear decay. So we started off talking about rate laws as a relationship of how fast a reaction is to the concentration of the reactants. So this numerical value is going to also help relate our two variables in a reaction. Rate constant is going to be different for different reactions. It's never the same for two different or more reactions. Larger values of K tend to mean reaction proceeds more quickly or is faster. What would a small value of K indicate? Probably the opposite. You guys probably figured that one out. You're good. Any questions on the rate constant? Okay. So these rate laws, our goal here is to figure them out and figure out what the rate constant is, determine the orders or those exponents of the individual reactants, and then obviously get the overall order. So all rate laws are always determined experimentally. There is no book, there is no chart. You cannot look them up. You have to take your reaction into a lab, run some experiments in order to figure out what the rate law is as well as the rate constant. So it is always, always empirically determined. Rate order is also defined in terms of a reactant, not product concentrations. So when we write these rate laws, again, we are focusing on the reactants as we try and determine what the rate law is going to be. So here's a reaction of fluorine plus chlorine dioxide going to product. Little reaction there at the bottom showing you kind of what it looks like. My rate law is this. Rate equals the rate constant with F2 raised to the first power and ClO2 raised to the first power. We don't see the number ones because they're just assumed number one unless they are some other number, and then you can put that number in. Quick side note, the orders for us are going to be, should be whole numbers, maybe a 1/2. But in reality, keep in mind, with AP Chem, go to college, rate orders can be anything. They can be decimals, they can be fractions, they can be positive, they can be negative. They can be pretty much anything they need to be. For our purposes, we're going to go whole numbers, 0, 1, 2, 3, 4, 5, whatever. Again, we may come across a half order in the homework. You may come across a negative 1/2, 1 over square root, things of that nature. But again, mostly going to be whole number orders. So notice here in the reaction, it has a 2 in front of it. Notice here with ClO2, I said it was a 1. So what does that tell you? Are we getting our exponents from the coefficients? Well, no. Exponents are not the coefficients from the overall balanced reaction. We are not using those. They are coming from the rate determining step of the reaction. So, we talked about rate determining step last time, which is the slow step of the reaction. Now, you may not see the rate determining step, but again, please note, we are not using the coefficients as our exponents. Now, as we just said, coefficients come from the rate determining step. These are our exponents. So, our little catch-22. If our reaction is only a single step reaction, the overall equation is the rate determining step. Then, and only then, do the coefficients represent the exponents. You have to be told, as part of the question, the following single-step reaction, or the following reaction occurs by one step. You must be given some indication that the overall reaction given is single step, therefore it is the rate determining step. Then you can use the coefficient as the exponent. If you have none of that information, then you cannot use the coefficients as your exponent. Any questions? Alrighty then. So let's go through some steps that'll help us determine the rate order. So we write down our skeleton rate law, which we've just done before. Rate equals K times the coefficient, rate equals K times the reactants raised to some unknown exponent. Easy enough. Then we're going to look at some experimental data, which is going to be in a chart or a table that'll be provided to you. What you want to do is you want to find 2 trials. So there's usually going to be 3 or more trials provided. You're going to pick 2 trials that need 2 conditions. The first condition, the concentration of one substance is held constant between whichever 2 trials you are choosing. The second condition, the concentration of another substance is being changed. Now, how is it being changed? Doesn't really matter. It can be halved, it can be doubled, tripled, quadrupled, 1/4. It's some fractional or whole number multiplier in our case. But again, we need these 2 conditions in order to pick 2 trials to solve the problem. So we look to see how the rate changes when you vary the concentration of only one substance. So because one substance is constant, it is not affecting the rate. The substance that we are changing the concentration, we can say that rate is only affected by that one substance. Any questions? Okay. So, practice problem number 1. Here we are is our equation, which we saw before. And here's some rate data, where we see concentration for 3 different trials and the initial rate of those 3 trials. So, here's my generic experimental rate law. Rate equals K times the reactants raised to some coefficient. Sorry, some exponent. I apologize. This is my skeleton rate law. Questions on how I got the skeleton rate law? Okay. So, initially, looking at the data, I'm going to choose trials 1 and 3 because I'm trying to solve for fluorine. Notice that in trial 1, fluorine is 0.1, and in trial 3, fluorine is 0.2. So the concentration has changed. When I look at ClO2, trial 1 and trial 3 have the exact same concentration. So my condition has been met where ClO2 is held constant between two trials, and the one I'm focusing on, which is fluorine, is changing between the two trials. Questions on how I chose that? Alrighty then. So, highlight them. There we are. We just said that ClO2 stays constant. We know that fluorine is doubling, 0.1 to 0.2. Easy enough. Now, if I look at the initial rate from trial 1 to trial 3, by what factor is the rate changing? If you're not sure, or you can't see it, take the rate of trial 3 and divide it by the rate of trial 1, and you'll get your answer. But for our purposes, we can see that rate is doubling. Questions so far? Okay. So that's how we're kind of approaching what we're doing here. Now, to go one step further and solve the problem, I can say that fluorine, the concentration, is doubling, and I can say that the rate from trial 1 to trial 3 is also doubling. So I can show it like this, where 2 to the x, this 2 right here represents the doubling of concentration. The x right here represents this x, my exponent. And this other 2 represents the doubling of the rate. Well, I'm pretty sure you guys can solve 2 to the x equals 2. Therefore, x equals 1. So my order with respect to fluorine is first order. Any questions? Alrighty then. So again, here are steps for determining rate order again. We've already written them down. But I'm going to add one thing here. We want to figure out what exponent on the concentration change would result in the observed change of rate. That is the order. So when we do this type of math and we compare the change in concentration to the change in rate with one thing being constant, it's telling me what is happening or what is the order. All right, questions? All right, so still continue with question 1. We haven't finished it yet. So again, looking at the same one we already did with fluorine. Just another way of looking at it. So again, we know the order with respect to fluorine is 1. This is just another kind of quick, kind of down and dirty way, more so than we just saw in the previous example of going through it, but it's a way of setting up the problem. Questions again on solving for fluorine? Okay. All right, so we're going to add one more step. Repeat for each additional reactant. Okay. Well, back to our equation. Sorry. All right, back to our equation. We need to solve for ClO2. And here, we already know fluorine is 1. That's why a 1 is here to make sure I know I've solved for it. So, we're going to look at experiments 1 and 2, where we can see the rate quadruples. So, we're going to use a 4 in the place of rate, because 1.2 becoming 4.8 clearly is 4 times larger. Well, again, we look at ClO2. How is the concentration changing? It's 4 times larger. If we look at fluorine, how is the concentration changing between experiments 1 and 2? It's staying constant. So we know fluorine's not playing a role. So ClO2 quadruples as well. So I'm going to put a 4 in there for ClO2 as I have it right here. Okay. So fluorine is constant. We get rid of it. K is a constant, so we're going to get rid of it. We're left with 4 equals 4 to the y. You can solve for y. So the order with respect to ClO2 is also going to be 1, which gives me my overall rate law here in the red. Any questions? Alrighty then. Question 2. All right, have at it. Please raise your hand in Zoom once you have got your rate law complete. I'll pause it. Ready, set, go. Alrighty then, we are back. So we want to solve for the order with respect to A. Well, if I'm solving for A, I'm going to use trials 2 and 3. Again, A is changing, B is held constant. Well, if I set this up and do the work, I'm going to get 2 to the x equals 1. So the order with respect to A has to be 0 because the rate is staying constant even though you change the concentration of A, rate didn't change. So it has to be a 0 order. Basically means that A is not participating in the rate determining step. It doesn't have a role to play in the overall reaction rate. I want to solve for B. So I'm going to use trials 1 and 2, where A is held constant and B is being doubled. I look at the rate. The rate is also being doubled. So 2 to the x equals 2. B has to be 1, or the order with respect to B has to be 1. And then the overall order of the reaction, add up 0 plus 1, you get 1. What is my rate law? And here we go. Notice that the concentration of A is not included in my rate law. Well, what's anything raised to the 0 power? It's just 1. So anytime you have a 0 order, yes, you need to identify it as we did here, but in your rate law, you will not include that reactant. Any questions? Okay. Question number 3. Solve for all 4 of these problems and raise your hand in Zoom once you're done. Ready, set, go. Alrighty then, we are back. So, what is the order with respect to chlorine? I'm going to use trials 1 and 2. We see that NO is constant, chlorine is being doubled, and the rate is also being doubled. So 2 to the x equals 2, x has to equal 1. So chlorine is first order. Looking at NO, what 2 am I going to choose? Well, hopefully we're going to pick trials 2 and 3, where NO is being doubled, chlorine is staying constant. And looking at initial rate, again, if you can't see it, then just divide trial 3 by trial 2, and you'll see that rate is actually being quadrupled. So 2 to the y equals 4. Therefore, y equals 2. So it's second order with respect to NO. Well, overall order, just add up your individual orders. 1 plus 2 equals 3. Yay. And then my rate law, I get this. Again, normally you would not include the 1 with chlorine. You just leave it alone. Can you include the 1? Of course you can. It's just by convention, when it's a 1, we tend not to do it. Any questions on this one? All right. Practice problem 4. Determine the rate law and calculate the rate constant for the following reaction with the following data. Alrighty then. Well, I'll pause it. You guys have at it to solve for the rate law, and we'll come together and we'll talk about solving the rate constant after that. So all I need you to do right now is solve for your rate law. Raise your hand in Zoom when you're done. Ready, go. All right, we are back. So here's my skeleton rate law. Easy enough. So we're going to double iodine and rate doubles with experiments 1 and 2. Therefore, y is going to be 1 because 2 to the x equals 2. For S2O8, or experiments 2 and 3, we're doubling that concentration, and the rate is also doubling. So x equals 1. First order with both reactants. Here is my overall order. Any questions how I got the rate law? Okay. Now, in order to solve for K, all you're going to do is rearrange your rate law and plug in the numbers. Now, looking at the data in the chart, when you solve for the rate constant, technically speaking, you should be able to use any experiment and you'll get the same rate constant. It doesn't matter which one. I will say, however, if the question on homework or the quiz tells you to use a specific experiment, please make sure you use that one. So I'll rearrange my rate law to solve for K. I'm going to plug in everything from the experiment number 1. Easy enough. And I'm going to get my rate constant as 0.08 per molarity times second. So really got to be careful with your units of K. They depend on order, meaning the units for K, the rate constant, can change. They're never always the same unit. Different overall orders, you're going to get a different unit of K. Need to be very careful with what's going on. Questions on this? Okay. All right. Big note here on our steps. If you don't have 2 trials that hold everything, but one reactant constant, easiest thing is solve for the orders that you can, and then pick 2 trials and plug in the values you do know to determine what you couldn't figure out. So if you go to solve for one and nothing's constant, solve for the other thing. Get as much information about your rate law as you can, and then you can start solving for those unknown things. And it may be helpful to do it that way. Questions? Okay. So, what counts as showing my work? So, what I'm looking for. What trials are you using? I'm using 1 and 3. Which concentration is held constant? Hydrogen, for example. Which concentration is being changed, and by what factor is it changed by? Oxygen is being doubled. That's why there's a 2 there. What factor is the rate being changed by? It's doubling, or quadrupling, or tripling. 1, 2, or 3, 4, whatever. And then the order based on the rate data. So my answer is order 1, 2, 3, 0, this type of thing. No, it does not need to be in a chart format that you're seeing here above. It just needs to somehow convey how you got your answer. I need to know what you're doing. Do not need to show the math to show doubling, tripling, etc. unless you really need it for you. If you can see that rate is being doubled or concentration is being doubled or tripled, that's pretty clear. But when you are calculating the order, showing me 2 to the x equals 2 or 3 to the x equals 9, I need to see that type of math. When calculating the rate constant, you do need to show the math. Show me what you're plugging in, which experiment you used. Need to know what numbers are being used to solve this problem. Questions? Alrighty then. Thank you very much. Until next time.